So if we remember in chapters 6 and 7, we discussed discrete and continuous random variables and their distributions, which is binomial and normal distributions. In this chapter, we're going to continue this discussion of the probability distributions where statistics, such as x bar, which is the mean of a sample, the mean itself will become the variable. So we're adding another layer to what we've been studying. Before today, we were finding the mean and seeing that the data was normally distributed, but we can also extend this to actual statistics. Remember, statistics become random variables because the value of a statistic can vary from sample to sample. For this reason, statistics have a probability distributions associated with them. We will use probability distributions to make probability statements regarding these statistics. So this chapter discusses the shape, center, and spread of statistics such as x bar. So instead of just looking at a set of data, people's IQs, and taking a sample and finding the normal distribution of that sample, we're going to take thousands of samples and find the distribution, the shape, center, and spread of those 1,000 different statistics. So we're adding, again, another layer of our study if we were studying something and trying to do the statistics of it. So the first vocabulary word today, the sampling distributions of the sample mean. The sampling distributions of the sample mean, x bar, is the probability distribution, which is what we studied last class, of all possible values of a random variable x bar computed from a sample size n from a population with mean mu and standard deviation sigma. The idea behind obtaining these sample distributions is as follows. You're going to find a simple random sample of like size 10, find the mean of this random sample. Then you're going to find a new sample of size 10 and find the mean. If you find a sample of data from one set of 10 and another set of 10, are they going to have the exact same sample mean? Like, let's say, okay, we're trying to see a population of Mesquite High School to see how many people drive a car. I asked you guys, how many of you drive a car? You answer, I find the average. I then go across the hall to Miss Caldera's class and I ask them, how many of them drive a car? Are they going to have the same exact number of people who drive a car in that class as we do? No. So we have a new mean from that population, Mesquite High School students. So what we're going to do is we're going to repeat our skills that we did in the previous two chapters many times to then make a distribution from those summaries over and over again. So our example 1 here, an intelligence quotient or IQ is a measurement of intelligence where the scores on this test are approximately normal with a mean score of 100 and a standard deviation of 15. That's for the population. What is the sampling distribution of the sample mean for a sample of size 10? Okay, so remember the sampling distribution of the sample mean would be the distribution of all possible sample means size 10. To get a sense of this distribution, we're going to simulate 1,000 samples of size, oops, that should say 10. Fix. Embarrassing. That should say 10. For each of the 1,000 samples, we're going to determine the mean of those samples. We're going to use Excel to create a histogram of these 1,000 samples and to determine the mean of the 1,000 samples and to determine the standard deviation of the 1,000 samples. Just so you remember that standard deviation, the formula here is sigma equal to the square root of the sum of x1 minus x bar squared divided by n minus 1. Because we're doing this for a sample instead of a population, we have to subtract 1 for the degrees of freedom. This is a formula from chapter 3 that we're using again here. So on your Excel workbook, that we have for this section, I'm going to try to go slow because I'm going to teach you some new shortcuts here. When you open it, you'll notice that we have, bless you, IQ samples, 10 of them in each row. Okay, so we asked people to tell us their IQs, and how many times did we do this? Well, watch how I start to scroll. how many rows, wait for it, wait for it, wait for it. How many rows did I use here? 1,001. The first row is a title row. So how many samples did I take? I took 1,000 samples of size 10. So I asked 10 people their IQ 1,000 times. Now, obviously, if we go back to the top, we can find the average, the mean of one sample very easily. What's the formula on Excel to find the mean? So we're going to go equals AVERAGE, and we're going to open a parentheses, and we're going to go select those rows. Now, I want you to do this trying not to pick up the mouse, which means after I open that parentheses behind average, I'm going to use the left arrow to scoot over to the first number in that row. So I'm going to A2. To give Excel a range of cells, you're going to hit the colon button. So shift colon. And then you see how it already typed A2 for me again? I'm going to hit the right button to extend the little block to get from row A or column A to column J. And you see how the formula has adjusted to say A2 colon J2? Close parentheses, enter. So what is the average of that first IQ sample? 93.9. Okay. We know that our population, the mean is 100. So this one's a little bit below the average for the entire population. Now that makes sense. Now when we did this, what would we have done to copy this formula to all of our samples? With a little square and drag it down. Well, this part's annoying, especially on y'all's tiny little screen. So I'm going to teach you a new shortcut. How did y'all, so it opens different on my computer. How did y'all get this to open in Excel?
You click on it and open with, and then Google Sheet.
Click on the very top and there should be an open with. How did you get Microsoft to show up?
Copy and paste.
Oh, you just opened a new Excel and copy pasted the data? You could do that. That works too. Google Sheets essentially works the same. But I know that if you go into actual statistics software and like studying statistics in college, they're going to use Excel over Google Sheets. These formulas that we're using are essentially the same though. Okay, so if I wanted to copy this all the way down, you would have to click on the little edge and drag all the way down. Instead, while you're in this L2, I want you to click Control Shift End. End. Do y'all have an end button on your keyboard? It should be, I think, on your top rows. Ooh, I just forgot that you're on a Chromebook. Do y'all have an end button?
No.
Ah, okay. Well, that stinks for you. Well, then you're going to have to drag it all the way down.
Okay.
That sucks. But if you're on a regular keyboard, after you Control Shift End, you can press Control D and it copies the formula all the way down, which is really nice.
Say Control D.
Control D copies the formula all the way down. How we doing? How we doing? Okay, so we have a whole bunch of averages for all of these 1,000 samples that we took. We learned how to do this before in chapter 3, just finding the mu of a sample. Well, now we have a whole bunch of mu's that we need to figure out the average of. So I'm going to go back up to the top of my screen just so I'm up at the top. And I want to compute the sample distribution, the sample mean. So I'm gonna label this, I'm gonna say the mean of the sample, and I'm gonna press equals the average. Now this time, what am I taking the average of? What column do I want to find the average of? L. So what we can do, and this is another shortcut for you, because the only information we have in L is all of those averages, yes? So because there's 1,000 lines of data, that'd be really annoying to, again, drag to the bottom. So we're going to press L:L. What that means is it's going to select all of column L and find the average of any number in that column. You do have to make sure that you have no extra stuff if you're using an entire column to throw off this average. but the way we set up our spreadsheet, we're good. We press enter, and we have the mean of the sample distributions being 99.6.
What's that?
Hmm?
Seven. Did you round?
99.7, correct, yes.
What was the formula?
It's just average, again. Average from L to L. Let's find the standard deviation. Now this one requires us to do a little bit of work. You guys wrote down the formula on your notes. It's that square root of the sum of x minus x bar squared divided by n minus 1. So here's what we're going to do. We're going to use this column m. We're going to do two things at once because we've been doing this long enough where we can do both the x minus x bar squared. So we're going to do two things at once here. I'm just put a label at the top so I knew what I was doing. For this formula, we want to take the average that we got, well, let me put parentheses. The average that we got for that row, so L2, we're going to subtract the sample mean. What cell has the sample mean for us right now?
P1.
P1, that's where I put it. So I'm going to put P1. I'm going to close the parentheses and I'm going to square it. We're doing two things at once. In chapter 3, I made y'all do two separate columns for this. We can do this all at once. Now, if I were to drag this to the very bottom, it wouldn't make P1 sticky. But you know I want to use that mean value for every single one of these formulas. So I'm actually going to go back into, up here, the bar that has the formula, and surrounding the P and the 1, I'm going to put dollar signs. So shift 4 and shift 4 surrounding the P. I don't actually know if it's called the sticky key, but that's what I like to call it because it looks like an S. It's a dollar sign, right? But it kind of looks like an S. It makes that row and column sticky. Meaning when I drag this formula down, it doesn't change from P1. Look, this one says I'm going to do L3 minus P1. I'm typing in it. L3 minus P1. If I do it one more time, it's going to be L4 minus P1. But P1 has not changed because you put those sticky symbols. If I wanted to copy this all the way down to the bottom, I press Control-Shift-End, which I know means you guys are going to have to go all the way down to the end of the data. I make sure only column M is selected, and then I press Control-D, and it's going to copy that formula all the way down. I know you're going to have to drag because I forgot your keyboards don't have an end button. Wait, does the extended keyboard have an end on it?
No.
Julian says yes.
Oh, yeah.
Okay, there you go.
You should turn on
All the way down?
Yeah, all the way down to 1,000. That's why I'm pausing because if you're having to use the keyboard for the, or the mouse for this, it takes a minute. Yeah. Okay, great. So I press Control-Shift-End and see how it's selecting all of the data. And I typed something in column P, which is why it's there. So while still holding on to Control, while still holding on to Shift, I'm hitting the left button to kind of like back up and only select column M. If you hate all of these keyboard shortcuts, you can use the mouse. I just think it's kind of annoying to have to do that over and over again. Okay, so let's keep going on our standard deviation because remember, that's what we've been trying to find here is standard deviation. So our formula said we will do the square root of the sum of all of this stuff squared, which we just found, and then divided by n minus 1. So we can do that all in one fell swoop. We're going to do equals the square root of, double parentheses, the sum of what row or what column? What column do I want to do the sum of? M. So M colon M, close parentheses, and I'm going to divide that by n minus 1. How many samples did we take again? 1,000. So what number should I put in my formula? 999, because I'm doing 1,000 minus 1, close parentheses, and enter. What does it tell me that the standard deviation is? 15 for the population, but for my sample distribution, what is my standard deviation? The number that we got off of Excel.
Oh, 7.5.
7.5. Again, I'm doing a whole lot of steps in one cell. If you would rather go back to how we did this in chapter 3, because you're rocking it doing this with multiple columns, please go ahead. I'm doing the same stuff, just kind of quicker. Because we have 1,000 rows, it's a lot easier to do it in fast. Okay, the last thing we need is a histogram so that we can see the sample distribution. So what I want you to do is I want you to select column L by going up to the very top of L and clicking like that number. How did we add a histogram? Insert, histogram, and then that first one. We have our data. What does this shape look like? What is that called? Bell-shaped. So it's normally distributed. We're finally ready to write something on our notes. Okay? On our notes, it has a spot for us to look at the shape of the sample means, which is what we found. On your notes, I have the population distribution, which is what they told us in the problem. After we did all of this data work with our sample means, we also see that that histogram is pretty normally distributed. So we're going to call that approximately normal. I'm using the mathematical symbol for approximately, which is a squiggly line. Our center, our mu, which really should be x bar, we found to be 99.7. Our spread, our sigma, standard deviation, we found to be 7.5. What do you notice about the mu of the actual population and the mu of my sample mean? They're really, really close. Theoretically, it should be the same. And if I rounded that to just a whole number like this one, it would still be 100, correct? So really, our center should be 100. So our center of our normal distribution is at IQ 100. The population distribution and the distribution of your sample means should have the same center. It will always have a different spread, but it should have the same center, which is something very interesting. We're going to pause here before lunch because I know that first bell already rang. If I lost you somewhere in the data, before we start this again after lunch, we're going to catch you back up. So I know you took a long time doing this first example, but we're going to do this idea again. On the second page this time, though, it wants us to do this where our sample size is 25, which means each row that we're taking the average of to begin with is going to have 25 entries in it instead of 10. So if you notice on the document that I gave you, there's a second tab at the bottom. And I already found or generated the 1,000 samples for you. Again, you're welcome. So you guys lead me through this. If we want first to find the average or the X bar for each of these samples, what's the formula I use in, this is going to be cell AA2. What do I write?
Huh?
Wait, this is the second sheet you have in
The second sheet, yeah, go to the second tab. Because this one is, again, IQ samples, but each row now has 25 entries in it instead of 10. We're going to see what happens when we extend our sample size. So we're going to do equals what? Average, good. And then what cell does it start on? C2 all the way through. Wait, no, not C2. It should start on A2, right? Oops, A2, I just scooted over. A2 to what? To Y2. Cool. There's the average of that first sample, 104.8. We're going to copy this formula all the way down for all 1,000 samples. So you can drag the corner box if you want, or you press Control Shift End, which is on the external keypad. We found it. You have to turn on the number lock. To copy the formula, you press Shift D. Just kidding. You press Shift Control D. I messed up. I got to try it again. Control D is copy formula. So it copies that formula all the way down. You can press Home, which I think is on your external keypad, to go back up to the top, by the way, if you're wanting to do that fast. So let's find the average or the mean of this data of your sample mean. I hear a question. Gabby, what's your question?
Wait, under X bar is just average?
Correct.
How do I check it all the way to the bottom?
Are you on Sheets or Excel?
On Google Sheets.
Google Sheets, unfortunately, I don't know the shortcut on Google Sheets, so you just drag the corner all the way down.
Okay.
And I don't have the patience to do that, which is why I looked up the shortcut. But you do you. We're going to do the mean of all of those samples.
Close Control Shift D
Because I got a
for
different
language.
average number.
For the first one, what's up?
Is Control D.
To copy formula, yes.
Why does that look
It should be okay eventually because it should all average out. We're going to do the sample mean, or the mean of the sample means.
Mean of sample mean?
Mm-hmm. So we're going to do the average of the row AA to AA, which means take the entire row column AA, and find the average all the way down. We're able to use this shortcut without using the numbers because the only thing in column AA is these averages. Yes.
Well, I don't have room to do the other.
You need more columns.
Yeah.
Click up at the top. Right click up at the top. You should see Insert.
Oh, okay.
Google Sheets likes to cut you off when it thinks you're done with the worksheet. Excel won't do that.
Craziness. Well, there's a finite number of
So question, what does this mean that we get for these sample means?
100.
Is that good?
Yeah.
Yes, because the mean of our sample means should be the mean of the population, which the problem told us IQs have a mean of 100. If we're doing the standard deviation, which we do want, we need a row that gives us x minus x bar squared so that we can calculate the standard deviation. So in that column, we're going to do equals parentheses AA2 minus the sample mean, which for me is in AE1. Close parentheses squared. But before I drag that down, what am I going to put around the letters AE?
The sticky.
The stickies. What was the sticky key? What do I put there? $sign. So we put a $sign around the AE to tell it to be sticky on column AE and on row 1. I should really look up the correct word for that, but I like saying the word sticky. It's kind of fun. All right. And square it. So we go Control Shift End, make sure we're only highlighting a row AB. Control D copies that formula. Going back to the standard, say again?
AB.
For me, it's AB. Following the formula for standard deviation, we're going to take the square root of the sum, so SUM, of column AB to AB. So we want the entire sum of that column, because the only thing in that column is the x minus x bar squareds. And then we're going to divide that by n minus 1. How many samples did we take? We took 1,000 samples. So we used 999. So my formula up here, if you want a clean version of it, it's here in my formula bar. So it's the square root of the sum of column AB divided by 999, which is n minus 1. What froze? Your Excel froze? In what way?
It's just,
Does it say exit page? It happens. You're working with a lot of data here. So if I wanted to see the histogram here to see what's happening, I go select the AA column, go to histograms, and I can see what's happening. What does this distribution generally look like?
Uniform?
Uniform would mean they're all the same height.
Oh,
Bell-shaped, also called, starts with an N. It is sort of symmetric and bell-shaped, but now we can call it starting with an N.
an N?
Mm-hmm.
I don't know. Know that word?
Normal. Normal. Thank you for your honesty. So here, back on our notes, we're finally ready to do something with our notes. We're again going to draw the sample mean. Our shape is still approximately normal. The X bar is still 100, but if you notice the spread, which is that standard deviation, what number did I get for my standard deviation?
Oh, no, 3.9.
3.9. Notice that our standard deviation when we did the population was 15. Our standard deviation when we did this with a sample size of 10 was 7 point something.
Yep.
Now that we've made our sample size larger, what's happening with the spread? We started off with 15 for everybody, 7 for sample size 10, 3.9 for sample size 25.
Oh,
So our conclusion is as sample size increases, standard deviation of the distribution decreases. Which makes sense because we're taking more people into account. They should be less spread amongst each of the samples. Should have less variation among each of the samples because we're taking more people in each sample to begin with. Now this was a lot of work, right? To find all of these things each time. We had to do stuff from chapter 3 and build all of these spreadsheets. So we've done a lot of statistics, we being mathematicians have done a lot of statistics to find these formulas that make this a lot easier. And in fact, the mean and the standard deviation of the sampling distribution of X can actually be simplified down a lot. The mean of the The mean of the sampling distribution of X will always just be the same as the population. So we're going to write that as mu of X. So that is the mean of the sampling distributions. It's going to be the same as the mu of the population. Easy. The same way we found 100 every time we did that. The standard deviation, however, has a different formula. When you're finding the standard deviation of X bar, you will take the standard deviation of your population and divide it by the square root of the number of people in your sample. So if we calculate this for our two experiments here, for the population in example 1, simple random sample size 10, the sampling distribution, just like the population, will have a mean of 100, which it did, and a standard deviation of 15 divided by the square root of 10. And if we quickly grab a calculator, which I know probably nobody did because I didn't warn you about it, there's so many supplies on our desk today. If we do 15 divided by the square root of 10, we get 4.7. If we go on and we try this again, when our sample size was 25, we still had a mean of 100 and a standard deviation this time of 15 divided by the square root of 25. Which you could do that one in your head. What's the square root of 25?
5.
15 divided by 5 is. This is pretty close to the experiment that we ran. Look, our spread was 3.9. So as we increase our sample size, we're going to get a smaller spread, and we can estimate that spread using the standard error of the mean, or that standard deviation formula. Also, we noticed as we did this experiment that the shape of our sampling distributions pretty much stayed normal when we had normally distributed data. So if the random variable x is approximately normally distributed, meaning your population has normal distribution, our sampling distributions of the mean will also be normally distributed, which means we can use our pink charts to find probabilities. Example 3 goes on from this. It says the IQ, which is our simple random variable, of humans is approximately normal with mu equal to 100 and sigma equal to 15. This is the same stuff from all day. Compute the probability that a simple random sample of size n equal to 10 results in a sample mean greater than 110. That means we're going to compute the probability that x is greater than 110. Since we know that this is normally distributed, all we need to do is figure out the z-score for this data and look at that z-score on our pink chart. Here's what we know. We know that the mu of x bar is going to be 100 because it should be the exact same as this. We know that the sigma of x bar will be the sigma of the population divided by the square root of our sample size. And I'm not going to calculate that number necessarily because I want it to be super duper accurate. So we're going to do a z-score equation that looks kind of wild, but you have a calculator for a reason. We can find our z-score for this data the same way we always did z-scores, which was x minus mu over sigma. That's the formula from chapter 7. The value I care about here is 110, Miss Quigley, get it together, minus this 100 that we have for our data, divided by the sigma that we have for our data. Same formulas, we're just now using the sample means to describe this. We always round z-scores to 2 decimals because that's what we have on our table. So 110 minus 100 divided by the fraction 15 over square root of 10, what do you get? 2.11. That's our z-score. The question here is, what is the probability that x is going to be greater than 110, which really means we're doing 1 minus the probability that x is less than or equal to 110. Since our data table, z-tables, standard normal tables, always tell us less than, we go to positive 2.11 on your pink chart.
This is 9.86.
0.98. I'm seeing 257.
2.1. Oh yeah.
0.98257.
Yeah.
If you subtract that, that is 0.01743. That's the probability that our sample mean would have an average that is 110 or higher. The probability of obtaining a sample mean IQ greater than 110 from a population whose mean is 100 is this 0.01743 or 1.7%. If we take 100 simple random samples of size 10 individuals of this population, about 1.7 or 2, depending on how you're rounding, of the samples will result in this mean IQ that is greater. Is that an unusual number to get? Well, like percentage in probability. Is 1.7 considered unusual? Yes, because 5% makes it unusual. 1.7 is definitely smaller than that. So we did all of these experiments on our Excel sheet to show you why or how we came up with these formulas for sample means, what we're even looking at when we're looking at a distribution of a sample mean. Okay, the main idea here, what you're going to need to be able to do is going back to these z-scores, making sure you know how to use them. So this example 3 is going to be very, very helpful, I think. Moving on. Now, of course, we started all of this with if a random variable x is approximately normally distributed. So a good follow-up question is, what happens if the data we're looking to work with is not normally distributed?
That's a good question.
Yikes. If it's not normally distributed, we're going to have to find new tools to use because everything we just did was based on already normally distributed data. So look at example 4. It says the data in table 1 represent the probability distribution of the number of people living in households in the United States. Figure 6 shows a graph of this probability distribution. From the data in table 1, we determined that the mean and the standard deviation would be 2.9 and 1.48 respectively. So we have the mean and the standard deviation of this population. How would you describe this graph? Is this normally distributed? No, it's skewed which direction?
Right.
Skewed right, because we have more stuff on the right. In fact, this isn't even a continuous set of data. This is discrete data. So we wouldn't have even been able to do a normal distribution for non-discrete data. That was only for continuous data to begin with. However, if we were to run a bunch of samples of this at different sample sizes, look at what happens to the data. Here's my sample size 4. Here's my sample size 10. Here's the sample size 30. What do you notice now?
It gets more uniform, or like it fits into the shape better.
It fits into the shape better, which means what's the N word we forgot earlier? It's becoming approximately normal as we increase the sample size. Let's look at what happens to our standard deviations. The formula we had for standard deviation said to take the standard deviation of the population, which was 1.48, and divide it by the square root of the sample size, which means for this first one, we're doing the square root of 4. 1.48 divided by square root of 4, which is 2, is 0.74. If we do the second one, 1.48 divided by the square root of 10, it's going to give you 0.47. For that last one, if we do, again, the sample size or the standard deviation of the population did not change 1.48, but my sample size did. 1.48 divided by the square root of 30 is 0.27. My standard deviation has done what as we've increased the sample size? Gotten smaller, which means we're less spread out. We're more accurate with our data with a smaller standard deviation. It's all piled up in the center, which is great for us because we have what's called the central limit theorem. The central limit theorem states that regardless of the shape of the underlying population, meaning it could be non-normal, it could be discrete, the sampling distribution of x bar becomes approximately normal as as the sample size increases. Bottom line here is if the distribution of the population is unknown and or not normal, then the distribution of the sample mean is approximately normal, provided that the sample size is greater than or equal to 30. I want you to put like a big ol' circle, maybe some exclamation points here. Sample size being 30 is key for us when we are doing data distributions because having a sample size of 30 or more means that we can assume that that data is normally distributed. And if the data is normally distributed, we can use our pink paper to find probabilities. Yay. This is what we want because usually with statistics, you're trying to draw conclusions about the probability of something happening. So we want our sample sizes to be 30 or higher for sample means. That's a big deal. Let's see one more example for today. before you get to stop listening to me talk. The mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9 pounds. Weight gain during pregnancy is skewed to the right. An obstetrician obtains a random sample of 35 low-income patients and determines their mean weight gain during pregnancy was 36.2 pounds. Does this result suggest anything unusual? Okay, so we have a whole bunch of samples to look at, and this obstetrician looks at one particular sample of 35 low-income patients. First things first, is this enough patients to look at to assume that we are looking at normalized data? What was the number it needed to be bigger than? I just made you circle it on the other page. 30. We're looking at 35. Are we good? We're good. The sample size is large enough for us to assume that it is normal. Or normally distributed, shall I say. Our question becomes, does this particular sample we get suggest something unusual? Which remember, unusual means outside of the top and bottom 5%. Okay, to do this, we need to know the mu of x bar, the sigma of x bar, get a z-score, thus find the probability. Here's the nice part. The mu of x bar is exactly the same as the mu of the population, 30. The standard deviation of x bar is that formula that we derived in this class, which will be 12.9 sigma of the population divided by the square root of my sample size. What was my sample size? 35. Again, I don't really care what this number is because we're going to be more accurate by using this ugly fraction with the radical in the denominator in my formula for my z-score. So we find the z-score. The z-score is always the number we care about, which in this case was 36.2 minus the mean of the population, or in this case the sample distribution, divided by the sigma of the sample distribution, which would be 12.9 divided by square root of 35. We always round z-scores to 2 decimal points so we can use our chart. You guys were really good at z-scores when we did this in chapter 7. So 36.2 minus 30 divided by 12.9 over the square root of 35. I see you calculating.
2.84.
Very good. 2.84 is the z-score. So we want to know if the z-score being 2.84 is something unusual. We're doing the probability that x is greater than or equal to 36.2 because that's the z-score we found. Since I wrote down greater than or equal to, do I just look straight at the table for the z-score or do I do 1 minus? For greater than? 1 minus. The table is always less than. So we're doing 1 minus the probability that x is going to be less than 36.2. So let's find that probability. On our table, 2.84, so we go to the positive side. We find the row for 2.8. We find the column for 4, and we line them up. I'm seeing 0.99774. So 1 minus 0.99774 would give me, which percentage-wise, because it might be easier to look at this as a percent, is 0.226%. That's the probability that we would find a random sample of 35 low-income patients with this average rate gain during pregnancy. So if the population from which the sample was drawn has a mean weight of 30, the probability, this is the conclusion sentence, is approximately 0.022, I did one too many, 0.226%. This means that for 1,000 samples, you're going to find only two samples that would result in a mean of 36.2 pounds or higher. So as a doctor, if you found this sample of women who gained this much weight during pregnancy, and that should only happen 0.226% of the time, that's when a doctor would be like, something's wrong here. This percentage of population, something is different about them. This is unusual because it's outside of the 5% rule. So we would go into the sample and we'd look at the women and we'd say, all right, do we need to change your diet and exercise? Do you have an underlying like thyroid condition? This is how doctors kind of decide whether something's normal or abnormal in your health history. The last thing you have here is a nice little summary. It's kind of a funny summary because if you notice the formulas just immediately looking over here, did anything change?
No.
No, the only thing that's really different here is that if something is normally distributed to begin with, you're good to go.
Okay.
But if it's not normal, then you need to make sure that the sample size is larger than what number? 30. You need to make sure the sample size is 30 or larger, and then you can use these rules. If it's not larger than 30, then we can't decide that it's normal and use our chart to do probability. We're about to draw these last few chapters all are about finalizing and drawing conclusions with data, which is going to be a lot of formulas and a lot of different names for data. So make sure you know what you're finding and what it's called. Labeling your formulas well is going to be very, very important in these chapters.